Hi everybody. Today we're looking at 3D part 2. So we're graphing first derivatives and second derivatives. Show my whiteboard. There we go. And I might be able to just zoom in slightly. Is that going to help? I actually want a bit of space. Maybe just make this 80%. For some little scribbles. All right, I'm going to do the first derivative in blue. This can be blue. And we'll do the second derivatives in green. Okay. So for first derivative, we know that we've got a downhill. We've got decreasing here in our function, which means downhill, which means negative gradients, up until we get to this minimum, right? This is a stationary point. Why is it called that? Because stationary. Why is it called a stationary point? Right? Because the rate of change of the function at that point is 0, right? So the gradient there is 0. Then we start going uphill. The function starts increasing. We're going uphill, and I need to try and draw a perfectly straight line through there to represent our first derivative. Our second derivative we'll go through about here, right? Our concave up shape, all right, you've got to link the ever increasing gradient here. It's always increasing. It's a concave up shape, and that means a positive second derivative. Hopefully you can see the order changing. So the original function had x squared, right? Then when we differentiate, we get x, straight line, and then we differentiate that and we just get a single number. Let's try and write an equation for the function. We could say y equals, that's probably just this, x plus 2, x minus 4. I mean, there's a potential for there to be some number here, a dilation factor for the parabola, but you know, not necessarily. So we'd have x squared minus 2x minus 8. If I expand this, what's the first derivative going to be? 2x minus 2. What's the second derivative going to be? So we can see how the order, right, we're going from x squared to x to the power of 1 to x to the power of 0. Right, just 2. Now, it might be interesting to stop and think, well, this parabola, does it really give us a second derivative that's constant the whole way through at y equals 2, we're thinking? You can see it in a table of values. If I might go from the turning point here. Now that's going to come in at x equals 1, halfway between the zeros. So if we were to go back to year 8 for a minute and look at a table of values for our function. I'll go up to 6, I think. So if I plug 1 into the original function, we do it here, I get 1 minus 2 minus 8, that's minus 9, minus 9. Then if I plug 2 in, I'd get 2 squared is 4, minus 2 times 2 is 4, so that's 0 minus 8. Then if I plugged 3 in, I'd have 9 minus 6 minus 8, it's minus 5. Plug 4 in, I've got 16 minus 8 minus another 8 is 0, which I didn't need to do because it's here on the graph at y equals 0. What about 5? 25 minus 10, that's 15. 15 minus 8, that's 7. 6. Now this should be, that's gone plus 7. The next one should go plus 9, so it should be 16. Let's check it. 6 squared is 36, minus 12, minus 2 sixes. That gets us down to 24. 24 minus 8 is 16. Good. So those were the y values in a table of values. The first derivative tells us the rate of change, or the change in those y's. And that would be, just looking here, we went from minus 9 to minus 8. That's gone up 1. Then we went up 3. Then we went up 5. Then we went up 7. Then we went up 9. And the second derivative is like if we looked at the difference of that difference, if we look at how does the rate of change, how does the gradient function change? Well, what's the difference between 1 and 3? What's the difference between 3 and 5? 2, 2, 2's all the way along. So we have this constant change in our gradients. All right. Now, obviously you don't need to do all that. Now, hang on, I didn't want to delete all of that. I just wanted to erase a bit. You don't need to know what the function is. I'm just looking at this in detail. Okay. B. So graphing first derivative first. There's a stationary point here. There's a stationary point here. Right. Now it might be useful in questions like this to draw sign diagrams. Oh, I deleted a bit of a line there. So for B, where can I draw a sign diagram? Probably fit one in here. Here is the first derivative sign diagram. It has a stationary point there. Now, if that's a minus 2, let's call that a minus 1. Looks close enough to minus 1, and then that looks like it's about positive 1, that stationary point, that local max, sorry, local min. So this is local max, that's a local min. Now here the function's going uphill, the function is increasing, the gradient is positive. Downhill, negative, uphill, positive, right? So we've got our local max, we've got our local min, right? So if we're going uphill with positive gradients, we need our function to be up there. Now the point of inflection will be at a minimum value, maybe whack it in about there. So, oh yeah, okay. So there's the first derivative, maybe not drawn as well as it should be. Okay. Now the point of inflection is identified when the second derivative equals 0. About here, I reckon it's right on 0. It's where we go from concave down to concave up, where we change our concavity or change our shape. If we're concave down, we've got negative. Just whack it through a bit, maybe like that. So if we're concave down, we have decreasing gradients. I can see it here. The gradients were getting smaller, smaller, and then became negative as well. Right? So we've got negative second derivative values. Then we have increasing gradients or positive second derivative. Okay, if I was to draw a sign diagram of that, the second derivative is showing me the point of inflection. Point of inflection looks like, to me, like it's right on 0 there. We've got concave down, negative, over here for negative x values, Then we've got concave up, positive. Negative. The gradient values are getting smaller and smaller, or towards the negative, right? Then the gradient values start increasing, right? Hence positive. Okay, now it doesn't say to draw the sign diagrams, but often it's a really useful thing to do when you're trying to sketch first and second derivatives. C, we've got a max here. We've got a min there, right at y equals 0. So that means first derivative will be 0 at those points. Here we're going uphill, we must have positive. That looks like a point of inflection there, where the gradient will reach its lowest amount. Then we've got downhill, so it's all negative. Then we've got uphill again, so we're going positive from that point on. So to sketch this, uphill means positive gradient values, negative gradient values, and then back to positive. All right, second derivative, okay, let's call the point of inflection about there. Maybe it's at x equals 2, right? Here we're concave down, so we're negative. Very similar to the last one, isn't it? And here we're concave up in the orange in the original function, so we're positive. Here, gradients are decreasing, right? So the change in the gradient is negative, it's decreasing, which means negative second derivative. Here, concave up, gradients are increasing, positive second derivative. All right, we finish on a quartic. We're looking for mins and maxes. Where's the min there? Maybe make it on 0 just for simplicity, it's about right. Then we've got a local max, then we've got a local min. All right, here we're going downhill, so here we're going uphill, we'll have positive values to that point of inflection. Let me draw that curve in there. All right, that point, we're back. So something like that. All right, that was our first derivative. All right, I'm looking for the min, make that a 0. This max, which that line should have come straight through that 2 there. It didn't quite. And then this min here at 4. Right, so the second derivative has to equal 0 there. We're going downhill. Right, that means negative values. We're going uphill, positive values. Downhill, right, negative values. Uphill, positive values. Okay, second derivative. Well, let's try and find these points of inflection. Here we've got concave up, that's concave down. So there's a point in here where we have a point of inflection where second derivative would equal 0. And there's a little point in there, so maybe about here. So this is concave down, then it changes shape to concave up. All right, now concave up means positive. It's going to be a bit hard to draw. There we go. Concave down means negative second derivative, and then concave up shape is positive second derivative. Okay, remember they're just a sketch. It's quite difficult for me to sketch on the screen with my little pen. But that's okay because it is just a sketch. All right, thank you, and I'm going to move on to the next question.